Okay guys, okay, let's focus on this example. Now we are given two conducting plates, alright, which position is shown here. So we can see from here, for the first plate over there is grounded, and this plate is positioned at phi equal to 0, and also the other plate over here is positioned at phi equal to alpha, and the alpha is any angle, and at here we have 100 volt potentials. So this plate having the width between R1 until R2, the length, and also have the height between Z1 and Z2, and then this conducting plate have certain conductivity value, sigma is shown here. So now we are going to find the potential equations, and then to find the E field, the D field, the charge density, and also the total charge, and also the C and R. So now, since we are not given any information regarding the charge density, so we can simply assume that this is a case of a free charge medium, whereby we can assume that there's no volume charge exists. So from here we can simply use the Laplace equations given as del squared V is equal to 0, and that's our Laplace equations. So to find these operations, or to find this equation for the Laplacian, you can refer to your textbooks, page 92, equations 3.51 for the case of cylindrical. So we know that, guys, for this case the only parameter that changes is only in phi, so it means that in R and also in Z they are remain constants. So if you look at to the expressions of the Laplacian given here, Laplacian's V is equal to the 1 over R d over dr R dv over dr plus 1 over R squared, and then d squared v over d phi squared, and plus d squared v over dz squared. So this is a full expression of the Laplacian operator for the case of cylindrical. So now again we know that this case we only concern on the phi component, whereby these two terms we can ignore straight away because they are remain fixed or constants. So we can have this equation 1 over R squared d squared v over d phi squared is equal to 0 from this Laplace equations. Alright, so now let's do the first integration for the both sides. The first one's over here and over here. So now we have dv over d phi. Integrate 0, we will have one certain constants. So now let's do the second integration for both sides. Again, we have here a v. Now a phi plus b. So now this is our general equations of potential. So we can find the exact or the specific value of the a and b using the boundary condition given here. So let's substitute the conditions. Let's say at phi equal to 0, so the potential is 0. So we put the value here, gonna have a 0, a0 plus b. So we know that the b now equal to 0. Okay, now let's substitute the second boundary conditions, where we have the conditions when at phi equal to alpha, and we know that the v now become 100 volts. So again, let's substitute the value of these boundary conditions into these general equations. So 100 equal to the a alpha and plus the b. We obtained earlier the b here is equal to 0. So now we have the a value become 100 over alpha. Okay, now we have the B value, we have the A value, so let's substitute into this equation. We have the final equation of potential is equal to the 100 phi over alpha volts. So that's the first expressions that we can find for the potential. So now let's proceed to the second part of the equation. We are going to find the E field, and the E field, guys, can be obtained from the potential expression over here. So the E is equal to negative grad V. Alright, again you can refer to your table of the gradient formula. From here, you're going to have a negative 1 over R dV over d phi, and now we have only in phi component. Again, we just focus on phi components because the only parameter that changed is in the phi. So now let's substitute the V. From here, you're going to have these expressions 1 over R d over d phi. So take it, the V term up there, 100 phi over alpha in phi component. So now let's differentiate this term over phi. So lastly, you are going to have this expression, a negative 100 phi directions or phi components over R alpha, and now we have unit of volt per meter. Alright, so you can get the E expressions as shown there. And now we know that, guys, from this E expression, we know that the E is actually propagating along the negative phi directions, because we have a negative here. So you can see from this diagram, we can simply draw your E field in these directions. Okay, and we know that from the E behavior, the E will always propagate from higher potential to the lower potential, or we can say that the E will propagate between positive charge surface to the negative charge surface. So we can simply note that at this particular plate we have many or positive charge. Alright, and over here we'll have a negative charge. Alright, so from here we can also proceed to the next part of it. We need to find the D field. It's simple, just finding the D field equal to the epsilon naught E, since we are dealing only with the free space environment. So just substitute epsilon naught. So you can again find the negative 100 epsilon naught phi directions of the D, and now R alpha, and now in this case we are going to have the unit of coulomb per meter squared. Okay, again, guys, the D also will go in the same directions of E, which is in negative phi direction. So here also the same direction of D. Okay, so now let's proceed to the next part. We are going to find the rho S value. So the rho S actually surface charge density that actually appear on the conducting plate surface. So the rho S, we know that we can find the rho S using this equation, D dot A unit vector. Okay, guys, so we know that the D as well given as a negative 100 phi component over R alpha. Now dot, now how do we determine the AN normal vector? So you can see from this figure, the AN is always following the E direction. So since the E and D in negative phi, so the AN also will go in the same directions, will be in negative phi directions. So you can put this dot with a negative phi direction. So finally we're gonna have to have the 100 over r, so the 100 epsilon over the r alpha. Again, you have unit of coulomb per meter squared, which we have here, epsilon naught, right? Alright, so that's the rho s that appear on the second plate over here. So how do you find the other plate? So just make it negative. So the rho s at phi is equal to 0. It's going to have here a negative 100 epsilon naught over r alpha. Again, unit of coulomb per meter squared. So this rho s appear at phi equal to alpha, which is positive charge density, and then this value actually appear on the other plate with alpha with phi equal to 0, right? So now done for the rho s, the charge density. Now we are going to find the total charge that exists or appears on the each plate. So again, the charge at phi equal to alpha, I mean the second plate, we can have from these integrations rho s ds. So now we know that, guys, the ds here is actually can be taken from this structure. Take a sample, so that's our ds, sample of area. So we know that the area for this structure is a square area, so just simply put for the z from z1 to the z2, and then for the r, for r1 and r2. Now we have the 100 epsilon naught r alpha, and then the s here, guys, we have the value of dr dz. So let's integrate over r and z. So we know that the r here is 1 over r, dr should have a ln term, so the q, total charge, actually is equal to 100 epsilon naught over alpha. And now for the z, we have here z2 minus z1, and for the r we have ln r2 over r1. That's going to be our total charge that appears or exists on the second conducting plate at here. Alright, so let's say you define here is your second plate, it's your first plate. Alright, so this is going to be your second total charge appear on the second plate, and it has unit of coulomb for sure. So same thing goes to the second. For the first plate, you can also find the same method. You can have same value but in negative sign, negative epsilon naught z2 minus z1 ln r2 over r1 over alpha, again in coulombs, right? So that's a total charge that appear at both conducting plates. So now we are going to find the next parameter, which is the capacitance. The capacitance can be defined as a total charge that appear on either conducting plates over the potential difference between these two plates, V naught. Alright, so if you want to take the total charge here, so you can take either one. So normally we take this one at 100 epsilon naught z2 minus z1 ln r2 over r1 over the alpha, and now over with v naught, which your potential difference, which is 100. So now we can simply just simplify deleting these hundreds. So now you are going to have the C expression given as epsilon naught z2 minus Z1 ln R2 over R1 over alpha. Alright, so that's the expressions of the C, and also must have unit of confirmed in farads. So now let's proceed to the last part of it. So now we are going to find the value of the resistance. The R can be obtained using these equations, the V over I. The V also called the potential difference, which is V naught. So you can simply put the V naught become 100, also can. So now the I obtained from the integration sigma E dot ds. Alright guys, the E, as we obtained earlier, the E expression is given as minus 100 phi component over R alpha. So let's put the value. Now we have negative 100 over this phi component R alpha, and now the ds also here guys, the ds, the ds here actually taken from this side and also half direction in phi. So again in phi here we have dr dz. So again we can simply delete this 100 because they are same. So now we can have the R equations. So now we have to integrate over the R, 1 over R dr, and also the Z. So now we're going to have the alpha is up there, the alpha, and also sigma. And here we have for the Z, we have Z2 minus Z1, and now integrate over R, we have a ln, it's supposed to be R1 to R2 now, since we are getting, so we have here R2 over R1. So that's going to be the R expressions for this particular. Okay guys, so don't forget we have a negative sign over here. So negative come from here, so you have a negative there. So if I want to make it in positive value, just rearrange this equation of R. So I have alpha over the sigma Z2 minus Z1, now ln R1 over R2. Right, so that's your final expressions for the R, the resistance, right? So I hope you can try yourself. So all the best and thank you.